Greetings, friends. Happy second class of the week. So we're going to talk about refrigerators today. We're going to finish up doing a little bit of engines and efficiency. We're going to talk about refrigerators. Still working on video quality, so work in progress, but hopefully most of it is coming through. And it's just really a matter of finding the right buttons to push. So there's little check boxes of stuff that are buried in other places. So hopefully the video uploads reasonably well. This week we have PLC 5, and like I said last time, that is a kind of mark it out and turn it in rather than a quiz style format, more of a homework style format. So let's see, where are we here? About there. So we'll do PLC 5, and that'll be for Friday as usual. But it is a maybe take a picture and turn it in style thing, or PDF it, or however you do it. So just watch the turn in part on that one. Issues with PLC 4, hopefully I fixed those, but I think I did, but I just haven't really gone back. Once again, I pushed the button and checked the box, and then I haven't gone back to see if that did anything. So I'll go through and check in on that. PLC 5 is Friday, homework 3 is Tuesday, and that's along with celebration 1. So this is this plus celebration 1, that's going to be Tuesday the 11th, so a little less than a week away. Tuesday. And lab, hopefully most of you managed to get in a lab proposal yesterday, so I can start reviewing them today. And I've talked to a couple of you already, actually you two. So I think we're good to go. Let me just check through and see how it goes. So let's put lab proposals were due yesterday, but anyways. And then that's going to be design your project. That's going to start this Friday. So this Friday to next Friday is when you get the time to work on the project. And videos due, what's this Friday? Next Friday. So it's the videos due the next Friday. So you get to work on it, and then video and presentations due the following Friday, the 14th. So that's what we got going on. We were in the middle of talking about efficiency last time, so let's continue doing that. And I have actually maybe we'll do this first. I have a little bit of a demo here for you. It's going to require a little bit of setup. So let me move stuff. And ultimately, as with all demos, especially the ones in physics, who the hell knows if this is even going to work? But maybe. Fingers crossed, and maybe good things will happen. So what I'm going to do is I'm just going to flip you this way and point you down at the desk that's right in front of us. And you'll notice here that I'm going to move the mouse. You'll notice here that I have a large canister. This is the liquid nitrogen dewar. You might be interested in the name of the dewar. It's called the Dewar, D-E-W-A-R, after Sir James Dewar, who invented this thing. And let's see. Oh, you can kind of see. Oh, this goes this way. You kind of can see. All right. We'll see how we do. Now this is the network computing lab that I'm in, so probably pouring this is not the best idea. So we just had a little bit of this left over from Monday, and let's see if I can just pour out a little bit here. this down. This is liquid air, and it is boiling rapidly. In fact, a lot of people would say, look at all the steam. Of course, we are more advanced to know that this is not steam. This is just fog. Steam would be invisible. Nonetheless, it is signifying that something is very cold. And so I'm going to try here to see if we can watch that droplet as it moves. And there it goes. This is obviously not a level desk. Because the movement of that droplet is interesting. Let's try this again. Don't try this at home without proper safety gear. All right, so let's wait for the fog to clear off a little bit. I'll start it over this side because apparently, you see, we'll look at him go. Yeah, this is the effect of what's called Leidenfrost. And if I were to be ridiculous and do very silly things, then maybe, and it's not showing up super well. Maybe you can kind of see the droplets moving around. The liquid air, as it turns out, is about 200 centigrade below zero. And since this is a video and you can go watch it again at your leisure, what is happening here, I thought we'd just take a minute to talk about it because thermodynamically it's rather interesting. What's happening here is that since air boils at its around minus 200 centigrade, which is really only about 70 Kelvin above absolute zero. So this is cold-ish. What happens is when you put it on the table is at, I don't know, 15 centigrade. It's 215 degrees above the boiling point of air, which means that it's kind of similar to taking water and putting it, which would boil at 100, right, and putting it on a table which is heated to 320 degrees, 315 centigrade, right? That's hot compared to this. So when I pour the liquid air onto the table, it's like pouring water onto a 300 degree skillet, centigrade skillet, right? When you get the droplet, what happens is, I'll just do a time lapse going this way. What happens is you get the droplet and it's formed like this, okay? And it's of course rather cold. Whereas this temperature is around, say, 15 centigrade. And then what happens next time slice over here is that some of the air boils really quickly right down underneath here because it's in contact with something that is way above its boiling point. So what happens here is this much is left of the liquid. Let me kind of darken that in. This is left of the liquid. And underneath it, if you can kind of tell that. No, you can't. Let's try and make that bigger. All right, now we're going to go with really big droplets. And they're going to be square. All right, so here's our droplet. And so the next thing that happens is it's the liquid still here, right? Now the liquid would be boiling as I'm going to make this even bigger, as it's in contact with a really hot desk here, right? And I was saying this is around 15 centigrade. So it boils and becomes vapor, becomes a gas under here. and this is a liquid. And the gas does two things. Number one, it causes the liquid to be able to move around. It causes this whole thing to be able to move around on the table as if it's frictionless, because it's essentially like a hovercraft. It's riding on a cushion of air. And literally it's air because this is liquid air, so the liquid's boiling and becoming just air. And so the gas is cushioning the liquid as it moves around, so it can move without incurring any type of friction on the surface. And also, it's helping to inhibit heat transfer from the very hot desk into the liquid. So it helps prevent the boiling of the liquid further, because gases are such bad thermal conductors, right? So the heat that would be going this way, which boiled immediately the lower part of this liquid droplet, turns this into gas, and now it's not getting through quite as quickly. So the lifetime of the droplet as it moves on the table is actually much longer than it would have been normally, just based off thinking about heat transferred in and what it would have taken in order to boil this whole droplet into gas. So this is known as the Leidenfrost effect. And so that is an interesting bit of an application of some of the things we've talked about to this point. The gas here is basically trapped by the weight of the droplet. And so it kind of compresses it a little bit and cushions it. And it really is like riding on a hovercraft. So it's just motoring around like that and not boiling quite as quickly. Now, certainly the air out here is also at 15, so it's putting heat into the droplet, but remember, the conductivity of the gas is not very high compared to a liquid or a solid, okay? So I don't know quite why it's called Leidenfrost. I never got to looking up where that word came from, but anyway, it was first noticed with water droplets on very hot plates. The same thing will happen. The water droplet will, the bottom of the water droplet will flash into a gas and cushion the water droplet, and you'll find the same thing if you ever heat a skillet and leave it on for a while and then pour a little bit of water on. You'll see this exact same phenomenon as what just happened there on the desk. So anyway, hopefully you enjoyed that. That was a bit of fun with liquid nitrogen. The remainder of which we'll probably just, I don't know what we'll do with the remainder of it. But anyways, the good thing about this is even though it's a liquid, it doesn't actually wet anything, which is pretty fun. So you can spill it all over paper and it doesn't actually get the paper wet. So that's kind of groovy. Okay, so last time we were talking about efficiency, and we were talking about engines and how to get the Carnot efficiency, and I think that's where we left off. So let's pick up here. With the Carnot efficiency. Which is denoted with a C typically, and this is 1 minus T. So it's 1 minus TC over TH. Let's see, how are we coming through here? Looking all right? I've noticed that if I turn the lights on high, then the glare on the whiteboard is not as bad. So let me know if there's some spots where there's glare that you can't see, but I'm not seeing anything that's really bad right now. So that's the Carnot efficiency, and this is certainly, remember this came from a heat engine, so this is only for a heat engine. I will say that, and I think I said this at the beginning of last class, that yeah, we go through lots of equations, right? We really do, and you know what? You don't need to memorize all of them, so please remember that I would much prefer that you think through first law reasoning and second law reasoning and how to apply it to an ideal gas using things like the energy bar charts, the piston cylinder drawings, and the PV diagrams. I would much rather you be able to go through that than remember that the Carnot efficiency of something is like this. Well, it's not that important. Starting with what the efficiency is, remember you should be able to just derive most of this stuff without too much of a problem because it's fairly straightforward in the sense that starting with the basic definition. Yeah, you need to remember that, but then ultimately you can probably get here. Let's do an example. Here, in which we have a cycle, a PV cycle. I'm gonna plot this for you here. Start here. I'm going to start here, up here on the PV diagram. We're going to drop down with an adiabatic expansion. So it's going to be fairly steep that way. So if I call this A, this is B, and then we're going to isobarically compress, which means we're going back here to point C, and we are now going to isovolumetrically heat. Go that way up here to get back to our original state. So this is a 3-process cycle in which here we have an adiabatic and Q equals 0. It's important that you label these, especially when you're just sketching like I'm doing right now, because to our visual abilities, it's not necessarily the case that we could tell an adiabatic from an isothermal just by looking at it with no other references. So if I call it out like this, helps to understand. Now, remember the basic schematic of our heat engine is that we have a hot reservoir and a cold reservoir, and there's heat going this way and this way, like so. Work is coming out. Now, there's definitely work done by this engine, because you can see the area in here is not 0, right? Now, what about where the heats are going to be transferred? I know I need to have a QH input from a hot reservoir. I know I need to dump the QC into a cold reservoir as the exhaust. The question is, where are we going to be doing that? Well, the good news is it's not going to be this one. No heat transferred there. So I've got two processes, and all I got to do is figure out which of these go here. So take a quick look at that and we say, okay, I kind of already gave it away, but going from C to A involves an isovolumetric process. And just by eyeballing where the isotherms are on this diagram, you would know that C is at the lower temperature and A is at the higher temperature. Therefore, this is a heating process, and that right there is QH going in, and therefore QC must be getting dumped as the process goes from B to C backwards this way. Out comes QC there, the cold heat drop. All right, so we're going to say, well, let's put a few numbers down in here. We'll call this V0 on the A to C line, and let's say we've expanded to 8 times that. 8 V0s out here is the volume at B, and we'll be interested in what's the pressure up here at B. It's at A. This is the pressure at A, right up there. Okay. So if we are going to do a calculation of QH, let's assume that we're going to look at a QH calculation here, and that the pressure up here, we know what this is. Suppose this is something like, I don't know, 10 atmospheres or something. All right, I'm interested in finding QH. All right. So how are we going to do that? Fortunately, this is a constant volume process, right? This is a situation here where I have the ability to say the input heat should be that. remember this is the molar equivalent of MC delta T, and we do have the ability where we have constant pressure processes and constant volume processes. We have the ability to write that as a molar specific heat transfer, right? So if I wanted to also find QC, I would have written that as CP down here times delta T, but this is a different delta T, so let me try and be a little careful with how I'm subscripting these T's. Let me put C to A here, and let me put B to C over here. Okay, so those are not the same delta T, they are delta T's appropriate to what the process is, right? This way and this way. Okay, so let's assume that we'll say that P at A here is 10 atmospheres. And if I'm going to look at N times CV delta T, then what we're going to need to know is, well, number one, is it monatomic, diatomic? What kind of gas is this? Okay, we'll go with monatomic. All right, so we'll put that in the list of givens here. Monatomic, and we will also say that, no, I guess that's pretty much all we really need. All right, so we're going to say here, if I've got an adiabatic from here to here, now at point C, let's see, I need to know, what do I need to know in order to get this? I need to know N, I need to know CV, and I need to know delta T. So if I take a look and see here, this thing for a monatomic gas is going to be 3 times 1/2 R, right? We would say that's 3 times 1/2 R. So I should be able to write this as 3/2 times NR and delta TC to A. Now, if you notice, NR times delta TC to A from here to here should be the same thing as if it was 3/2 delta of PV C to A. All right. What's delta of PV? Well, I need to know P times V for each one of these. That means I need to know P down here and V. Well, V is easy, it's got the same V. So what we've got here is this is equal to 3/2 P V, and that's at point C, minus P V, and that's going to be at point A. Well, VC and VA are both going to be V naughts, so those can go out. And PA, we know it's 10 atmospheres. Okay. Therefore, what I need to really find here is P at A, P at C, in order that I know the product P times V and P times V. All right. And I think I got those backwards now I'm looking at it. Right? Is this backwards because my delta should be final minus initial, and my final is A, so I've got the subscripts backwards. You know, why do I bring you people in here if you're just gonna let me screw stuff up on the board? That should be A, and that should be C. All right, that's better. Come on. I need to find P at C. So in order to do that, we're gonna go here. How do I do that? I need the pressure at point C, and that's going to help me find what this total overall heat's going to be. Well, fortunately, I'm going to notice something here. The pressure at point C is the same as the pressure at point B. But the pressure at point B is linked to the pressure at point A by an adiabatic. So I'm actually going to go backwards here. I'm going to go this way back to the pressure at point B, and I'm going to find the pressure at point B because I know how to get from an adiabatic A down to B. Okay, I know the pressure at A, and I know the volume at A. I know the volume at B. Now I just need to find the pressure at B because that'll be the pressure at C. So we're going to utilize the adiabatic process for this. And if you remember what's useful with an adiabatic, it's P times V to the gamma. So what I'm going to do is I'm going to take PV to the gamma up at A, set that equal to PV to the gamma down here at B. Okay. Looking for PB, so let's just solve this here. I don't need to worry too much about taking a gamma root, for goodness sake, so that's nice. This is going to equal PA multiplied by the ratio of VA to VB, that whole thing to the gamma. And A to B, that would be 1/8. I'm going to stop and make sure because you people aren't checking me that well here. So I've got A, am I doing this right? I've got A up here at the top, and I've got B down here at the expansion. So that VA over VB, that looks like 1/8 to me. All right. So we're going to do 1/8 to the gamma. And what's gamma here for the monatomic case? Monatomic gamma, just by way of remembering, it's the number of degrees of freedom plus 2 divided by the number of degrees of freedom. We already kind of decided on the number of degrees of freedom being 3 monatomic, so it's got 1, 2, 3. So gamma would be 5/3 for the monatomic case. Not going to be very helpful to keep this in atmospheres. So what we can do is change that into pascals. Since 1 atmosphere is about 100,000, so 10 is about 1,000,000, or if you like, this would be 1.01 times 10 to the 6th pascals. If you want to be so precise to have the 0.01 in there. And then times 1/8 to the 5/3. This is going to give us a number, and we now know this number. And this number of pressure at B is the same as pressure at C, and therefore I can go in here and calculate what this heat is. Okay. Let's see here. What do we have? I have pressure of about 3.2 times 10 to the 4. And that's of the Pascal variety. And then we're going to take that pressure into the expression for our heat here. And now we know pressure and volume at A. Pressure and volume at A. And we know pressure at C now. And we know volume at C is the same V naught. So I guess we need to know what V naught is. Let's just suppose it's, I don't know, something fairly straightforward like, I don't know, a liter or something. Maybe it's a thousandth of a cubic meter. Suppose V is, this is 1 liter. So that's 8 liters. We're gonna go in and then calculate all of that stuff. Okay, so if you calculate that, what did I get for that? I got about 1.5 times 10 to the 3. Since that's a heat, it's gonna come out in joules. All right. All right, so that'll be our input heat here. Let's go through, do the same process here for the output. We're gonna drop out QC. We've got the same thing going here, which I can transform in the same way, right? So I'm doing all this without actually finding any of the temperatures. The difference here is that CP is a little bit bigger than CV. This, you may or may not remember, is CV plus R. Which means that if I look at this, it just becomes kind of like, it's kind of related to the gamma, right? The gamma is CP over CV for shorthand. So ultimately, if I think about it this way, this CP is basically the number of degrees of freedom plus 2 times 1/2 R. So instead of being 3 times 1/2 R, it's 5 times 1/2 R because it's at constant pressure now. This is 5/2 R. And we could go through and do the same type of process to find the heat that's dumped out here at the into the cold. All right, now let's take a look here and go like this. I'm going to move this up. All right, so just so we get this calculation done, this is CP times delta T B to C. All right, so now we've done 5/2 NR delta T B to C, and that means I can once again replace all of that with 5/2 delta of PV, which actually turns out to be much easier in this case because the P is constant. Okay, so now I'm going to get 5/2, and since I messed up that one over there with the initial to final, now I'm going to be on super high alert to make sure I don't mess it up again, but I probably will. This has to be delta P, so I got to do final minus initial, so final has to be C, and initial has to be A, so that's got to be, and ultimately it doesn't matter, because I'm just going to take the pressure out, and I'm going to call that pressure B, and now it's got to be V at C, which is V naught, minus 8V naught, which is the volume at B. So volume at C minus volume at B, and this is disquieting because clearly this is going to show us a negative number here. Is that okay? Why is this coming out negative? I'm going to get something like negative 5/2 P at B times 7 V naughts. Right, so we're going to assume, as we did in the other case, that V naught is, say, 10 to the minus 3 cubic meters. And we could calculate that number using the pressure that we found down there. What did I get for that? I got about minus 550. About minus 550 joules. Comes out negative. Are we happy, or is the negative sign copacetic with what we're expecting? so let's take a look here in the schematic. I've got QC leaving the system. Here on the PV diagram, I've denoted QC as kind of getting dumped out. So if we're looking at system, this is definitely heat leaving. So heat leaving for us, that should incur a negative sign here. So this should be okay. All right. Let's see here. Happy days so far. Let's get rid of this. All right, let's take a quick look at the, let's take a quick look at an application of the first law. Okay, so we're going to take this cycle here and let's take a look to see if we can find out what is the work done completely, right? If we go all the way around the cycle. So first law, I always recommend considering and writing down the entire first law, even if you already know you're going to make some adjustments or some simplifications to it. The internal energy change is Q plus W. Now, if this is cyclic, right, I'm going to start at A, expand. I'm going to isobarically cool. I'm going to isovolumetrically heat and keep going along like this. Therefore, if I start at C or A or B, wherever I start, and I return to that, then my delta E internal should be 0 for the cycle. And that means that, as we have come across so many times before, Q is minus W, or actually, if you think of it this way, I'm going to put the minus over here. W is negative Q. Now, we ran across this a little bit yesterday with how do you determine what Q is? Remember, it's a net. Okay, so this thing here is really a sum of all the individual Q's going in or out, and you carry the signs with them. Okay, so therefore this would be QH. This would be, in this case, QH plus QC. QC, we already know, has a minus sign to it, which we would have expected anyway. So you can write this as QH plus QC, knowing that QH is positive as it comes in and QC is negative as it goes out, or you can take care of your personal negative signs and just say it's QH minus QC, knowing that I'm going to have that minus in there already. But you cannot double count. Well, you can, but that's going to louse everything up, so don't. Just choose one, okay? Choose one of those ways of doing it. If I take this QH minus QC here, I'm going to take, gosh, what was QH? It was something like 1500, and this is about 500. So I'm going to be looking at somewhere around 950 joules. I'm going to be looking somewhere like 950 joules for the total net heat that the system took in, right? It took in 1500 and dumped 550. So net that it received was 950, which means that must have been how much work went out because there was no change in the internal energy. All right, so therefore the work done is negative 950 joules. And that's work done by the system because it left. Okay. All right. This has been kind of all working up to the efficiency, where we're now in a place, well, we could have already, but we're now in a really good place to calculate what the efficiency of the cycle is. So let's do that. I'm going to drop this thing here. And then we'll do one other thing on the way to doing this. All right. Now, the efficiency here we know is W over QH. And you'd say, well, I've got this negative sign in the W. I've got a positive QH, so my efficiency is definitely going to be negative because of the sign of the work. Well, no. If you want to be an absolute stickler for this, the efficiency does have to come out positive. So we would, if you want, we need the absolute value brackets around the work. We know the work is what we want out, right? It's what we want out. The out is kind of part, at least the way I think of it, the out is part of the definition of the efficiency. Nonetheless, we don't want negative efficiencies, so make sure that we're going to do 950 of the joules divided by 1500 of the joules. Right? Did I say 1.5 or something like that times 10 to the 3? 950 over 1500. Wow, that's pretty good. That's a darn efficient cycle right there. What is that? Like 60%. That's really good. Let's see, I got around 62-ish or so, something like that. 0.62. Or 62%. That's really good when you compare the fact that I'm taking in 1500 joules of heat and I'm kicking out almost 2/3 of that is as work. Wow, I'm doing great. I thought what would be an interesting piece here to extend on would be to calculate what is the Carnot efficiency for this cycle, which is basically asking the question, how good could this cycle be? Okay. So operating between a TC and a TH, that means we got to go in and figure out the TC and the TH. The TC and the TH, we're going to find, I want to find E Carnot, which means I need TC and TH. And I want to compare the actual efficiency that's working to the Carnot efficiency, my best possible efficiency. So the TC is going to occur at point C, right? Now that I've erased the thing. If you think of the isotherms, look on your diagram, right? The highest temperature should occur at A. Yeah, highest temperature should occur at A. B is in the middle, and then C is the lowest of that kind of triangle-y kind of type looking thing, right? So it's A up here, C's over there, B's back here. And therefore, if I calculate T at C, that's not TC. That's gonna be TH. Okay, anyways, whatever. At point C, or at state C, no, actually it will work out. TC is C. Ha, that's awesome. I did get it right. At point C, I want T at C to be equal to PV divided by NR. We need to know something about the number of moles. I want to know at point A. I'm going to get TH. Same thing again, PV divided by NR. All right. So far, we have not needed the number of moles because we've been able to do these cute substitutions here with the ideal gas equation of state. But to this point, we haven't needed them and we haven't found the number of moles. So we can assume, for example, that we have like, I don't know, 1. That makes it easy. And so the pressure times volume at point C, this was the one where it was 3.2 times 10 to the 4, and the volume was 10 to the minus 3 cubic meters. So we're going to divide that by 1 times 8.31. And over here, for the volume, for the temperature at point A, I'll just put this in here, assume 1 mole. At point A, we're gonna do the same thing. We're gonna do P at A, which was 10 atmospheres, 101 times 10 to the 6. The volume's still 10 to the minus 3. 1 mole and 831 on the gas constant here. Alrighty, so let's see here. This is gonna end up with a 32. Oh, this is gonna be kind of cold. Good thing I only assumed 1 mole. If I did, right, this would be 32 on the top and a little over 8 on the bottom, which means I'm a little under 4. Somewhat on the chillier side. So let's suppose that's around 3.7. We'll go 3.7 Kelvin. That's the cold. Thank goodness that's the cold temperature. Here in this case, I'm going to get 10 to the minus 3 is going to make that into 10 to the 3. So this is 1,000 divided by 8, which is going to be about 125, say, a little more than 8. So say a little less, so maybe about 120 Kelvin. Wow, so the efficiency of this cycle could be really high. I thought 62% was pretty damn good, but apparently it isn't. But you know what? That's thermo for you. I'm gonna get rid of this too. Okay. So we're gonna do this. The Carnot efficiency is now 1 minus 3.7 over 120. 3 over 120, well, 3 over 12 is 0.25, so this I guess is 0.025, or I guess it's closer to 4, so it should be maybe 0.3-ish, 0.03. So this is this is a number that's around 0.03 or something like that. So the efficiency of this would be something like 0.97, 0.96 would be the possible efficiency. Wow. We're doing really well, if we could ever get to that. Cool, so we're doing about 2/3 of the possible efficiency that we could have. Wow, I did not see that one coming. Okay, good. Sorry if I got any of these numbers wrong. Seems like we're kind of in the ballpark, so hopefully that's all right. Okay, so Carnot efficiency, we did that. Regular efficiency, we did that. And then all the rest of that, notice that all the rest of this analysis was just P's and V's and just process stuff. So that should be pretty, hopefully pretty straightforward for everybody. I don't know if it is or not, but hopefully it is. And then we're tacking on to top of that, this part here of the efficiency and that part there of the Carnot efficiency. Okay, let's talk about refrigerators. Which ultimately, and let's talk about heat pumps. Oh, I shouldn't have erased that. Oh well. Okay, let's talk about refrigerators and heat pumps. Now, a refrigerator typically is written or drawn, a schematic of it, exactly like a heat engine. You just flip all the arrows. And it's the same thing with a heat pump. All right, they're the same thing. Okay, so we have a hot reservoir out here. We have a working, the working thing, whatever it is. We're putting work into this in order to make heat go this way. like so, right? It's the exact opposite. I mean, all the arrows are reversed from the heat engine, okay? So why is a refrigerator the same thing as a heat pump? Well, all you really have to do is think about what the, and I don't want to get into the habit of doing this. You can think about what the efficiency is. What is it you're trying to get? And what is it that you have to put in order to do that? So the efficiency of the refrigerator is not called the efficiency. The refrigerator. The efficiency of the refrigerator is not called the efficiency, it's called the coefficient of performance. Okay. Performance. The coefficient of performance. And in a nutshell, really quickly, that's because it's going to be greater than 1. But why don't we try and figure out what we think it should be? It's still basically an efficiency. What you want out divided by what you put in, right? So if this is a refrigerator, what is it that we are trying to accomplish with the refrigerator? Ultimately, the refrigerator is here, and the kitchen or the outside environment or room or whatever is the outside air, okay? So your goal with the refrigerator is to keep this at this temperature, because we don't have ultimately perfect insulation yet. That's what we need you people for. So let's get some insulation on this, but nonetheless, we are going to be losing some heat out to the environment. We're going to get some heat leakage from the environment in, which is then going to cause us to need to pump it out and maintain this cold temperature here. Alrighty, so if we're going to take a look at what the refrigerator wants to do, then we're going to pull the heat, we're going to pull the heat out of it and maintain this TC here, okay? What we needed to do that was to put the work in. In other words, the refrigerator does not function unless unless it's plugged in. So our QC is what we want, and our W is what we had to put in order to get that. Let's look quickly at the efficiency of the heat pump. And let me describe a heat pump for you, in case you are not familiar with these wonderful gadgets. A heat pump. Now, in the case of a refrigerator, we wanted to maintain this, and this was the environment. If we have a heat pump, this is the environment, and this is our house, the inside of it particularly. And we are going to try and extract heat from the cold outdoors and make it so that we can be nice and toasty inside the house. The heat pump is therefore doing the rather far-fetched thing of removing heat from a cold environment and dumping it into a warm environment to make the inside of your house nice and toasty warm. Therefore, what is it that we want with the heat pump? Again, we still have to plug the heat pump in, so the work is the thing that we're putting in, just like it was back here with the refrigerator. I'm putting the work in the heat pump. What I'm getting out though, my desired output here, is the QH. Yeah, so here, QH divided by W. Isn't this a great thing? Far-fetched, that you can pump heat from the cold outdoor environment, the nasty, wild outdoors, and put it into your cozy bungalow for a toasty evening, and you don't even need a fire. I was gonna say buy the fire, but what would be the point of having a fire if you have a heat pump? The heat pump's gonna take care of it for you. So you can put on your robe and slippers, grab a nice cozy chair and a brandy snifter and snuggle up to your heat pump rather than the cozy fire that you normally would. We're gonna turn these into we're gonna turn these into these are both coefficients of performance, not really efficiencies, but they're called the coefficients. We're gonna turn these into other expressions like we did with the heat engine. In other words, from the first law analysis of this thing, we would again be able to write that QC plus W should equal QH, yeah? First law analysis still tells us that what's going in should equal what's going out, and therefore we should be able to write this as the conservation of energy. First law tells us that, right? This is energy conservation. So, or if you like, QH minus QC is equal to negative W, all this stuff with the signs. Here what we can do is then rewrite this as QC over W, which is QH minus QC. And here we do the same thing. We could write QH over QH minus QC. Okay, remember, we want these quantities to be positive. So the algebraic signs of these, just if you like to ignore them, if you like to put the absolute value on them, whatever you might like to do, it's fine either way, okay? So, taking a look at what we're expecting here, QH minus QC in the denominator. Let's just look at this one. This one's a fairly straightforward example. I'm going to have some number in the top divided by that number, but less in the bottom. This is why we expect the coefficient of performance is going to be greater than 1. Okay, in other words, we're doing really well at outputting what we want, whether it be this or this, compared to what we have to put in order to get that. So this is why we have moved away from the word efficiency, even though it basically is an efficiency, because it's still what we want out divided by what we put in. The problem is we have this mental block that efficiency is between 0 and 1, and therefore when we get something like the efficiency of a heat pump or the efficiency of a refrigerator, and it turns out to be 5, some people have like a mental breakdown. There's a little spark that happens in the brain, and they go, hey, you can't have an efficiency greater than 1, so we got to call it something else, and then we call it the coefficient of performance. And typically this is a number greater than 1, and so is that. So that the work that you're putting in is small compared to what the heat transfers are, and this is fairly typical. This is a fairly typical situation. You don't typically draw very much power or energy in order to cause the heat to flow. All right, now if we converted these into Carnot efficiencies, Carnot coefficients, then you're playing a bit of a fun game. But for example, you could take a look at the efficiency of the refrigerator, QC divided by QH minus QC. And what we could do is factor QC out from everything on the top and bottom, QC divided by QC. And we'd end up with 1, and we would have incurred a fraction here, QH over QC. Like that. So depending on, and of course this goes away, so we can just do that. So depending on how you want to look at it, the QH over QC fraction minus 1 typically will be a number less than 1. But from the Carnot perspective, we had actually the reverse or the inverse of this, which we were dealing with yesterday when we talked about the heat engine. And if you recall from yesterday, we found that this ratio came about because we wanted to operate the reservoirs and the engine at the very bare minimum of entropy, which means that we didn't incur any extra entropy at all throughout the entire cycle. As we ran the machine through whatever, we pumped a little bit of heat into there, did a little bit of work, and dumped the rest of our little bit of heat out into there. That decreased the entropy of the hot reservoir. The cycle was reversible and did not increase the entropy at all. The leftover heat, and that's when the work came out, and the leftover heat that we dumped as the exhaust into the cold reservoir increased the entropy of the cold reservoir, but exactly the same amount that the hot reservoir had decreased. So the total entropy of the entire situation, the change in it, is zero. When that's the case, we're able to write that fraction equal to that fraction. And therefore, if I just flip that over, I'm going to get the same exact thing going on here. And if I then undo all of this factoring and I go back to here, basically all it means I'm doing is I'm replacing a Q with a T. All right, so to get to Carnot, to the Carnot, remember efficiency, I'm just going to call it the Carnot COP. We just replace Q's become T's, and therefore the COP for a refrigerator, COP for R for the refrigerator, is then TC over TH minus TC. This would be the best possible scenario for the refrigerator that is operating between the same two temperatures as your refrigerator, and you would hopefully see that that this is bigger than yours, because your refrigerator is not as good. It just can't be, because we're trying to shoot for the stars here. Okay, so, and the same thing goes for the heat pump. We just do the same kind of procedure, and you're going to end up with the coefficient of performance, the Carnot coefficient of performance for the heat pump, as being TH over TH minus TC. And that is the COP for the HP. Now, typically, I will put this forward as a bit of experience, I suppose. Typically, you find you can buy heat pumps. They are generally more expensive. They're quite a bit more expensive, at least last I looked, and that was several years ago. I don't know if the price has come down now, but this is the situation with so many technological, like, advanced devices, right? Some type of technologically advanced device. The upfront cost is, in many cases, somewhat prohibitive. However, when you are running it, you are barely trickling the work in order to get the cold to move to the hot. All right. So yeah, the situation is very, very similar to the LED light bulbs. Okay, so you might buy an LED light bulb. You might buy one, because they used to be like $10 a pop, right? As time goes on, the price typically decreases, which is good. But the incandescent, right? In other words, the Edison light bulbs, maybe $1 each. Pittance, right? Buy whatever you want. But if I'm going to buy light bulbs, if I'm going to buy LED light bulbs for my entire house, I'm going to find that it's going to be pretty costly. However, when you compare, number one, the amount of energy that is taken from the socket in order to make the light bulb give you the light, The LED is so much more efficient than the incandescent light bulb, and that is because you can't really get less efficient than an incandescent light bulb. It is a 5% efficient bulb device. Its main job is not to put light out, it's to put heat out. So it's really a 95% excellent radiator. Really, this is a perfect situation to think about, can I turn all the work that I put into something into heat? And an incandescent light bulb is basically the answer to your question there. That's the answer to what you want. You want an incandescent light bulb. An LED uses much less energy, but puts out the same light. So it's more efficient in its light putting out. Might be maybe 40, 50% efficient. Now, over time that adds up, but also contrast this. The LED light bulb has a much longer lifetime than the incandescent light bulb, by a factor of maybe 4 to 5. So right there, you're making half the money back, right? So the problem is that when you look at buying these things, you just see, oh, but you don't look down the road, because that's a very difficult thing to do. Putting out money for an upfront expense, it's tough to do. Even I know, yeah, and I am who I am, and I'm going like, oh, but these are so much cheaper. No, don't do it. Get these ones. And I still have to force myself to do it. But you know what? We're happy in the end, because we get the same light for less price over time. You just don't see it. That's the problem. Okay, so heat pumps are great. They really are very efficient. They're much more efficient than your natural gas burning furnace, which is just combustion and then exhausting a lot of the gases, which you don't want in your house. But away with those exhaust gases means you're dumping a lot of the heat of the combustion out into the environment and not into your house. So the forced air natural gas heaters are actually much less efficient than a heat pump. So anyways, plug for that for the future. We'll leave you, we're just about done today, I think. I'm gonna do one more thing here, and that's talk about how a refrigerator operates. What I'd like to do is talk about whether it is more costly to run your, say you have a refrigerator and it's out in an unheated part of your house. Okay, maybe it's in the basement, or it's California, we don't have basements. Okay, so it's out somewhere, maybe where you park the car or whatever, okay? The question here is, if it's unheated, then suppose that it's essentially the same temperature as the outdoors. Okay, suppose you basically have a refrigerator outdoors. Does it cost more money to run the refrigerator during the winter or during the summer? Let's take a look at that. All right, so we can tell this a little bit from the efficiency. Right, if I'm talking about money that I'm gonna have to put in order to run a refrigerator, then I'm thinking, what's the efficiency of it? Right, yeah, refrigerator. So what I'm thinking about in the coefficient of performance of the refrigerator is, if I have a less efficient refrigerator, I'm paying ultimately more money, and if it's more efficient, ultimately I'm paying slightly less money, all right? So what we want to examine is, to answer the question, is it more costly to run it in the summer or the winter, when it's hot out or when it's cooler out, is what does the efficiency look like? What does this coefficient of performance look like during the winter and the summer? So let's examine the summer and let's examine the winter. Now, the good thing about this is the temperature of the cold is the temperature of the cold. That's the temperature of the inside of the refrigerator. So that's not going to be changing. This is going to be your what, 3 centigrade or 5 centigrade or whatever you set the thing to. What if you like 40 Fahrenheit or something like this, okay? So in the summer, it's warmer, which means that the hot that's where I'm ultimately pumping the heat. I'm trying to take heat out of the cold and pump heat into a hotter environment. So in summertime, TH is larger, right? Because TH is essentially the hot part, that's the temperature of the environment, okay? Here in the wintertime, the TH is smaller. All right, so TC being the same number in either case, summer or winter, what you'd find is if I did TH minus TC in the summer, this TH being a larger number is going to mean this is larger. And if I look at TH minus TC here, this is smaller. In other words, the outdoor environment is closer in temperature to the indoor, the inside of the refrigerator. And therefore, this is a smaller number. The good news is I'm dividing by that. So during the winter time, this is a smaller number, and therefore my coefficient actually goes up. And I think hopefully this kind of makes sense, because it's way easier for a pump, for a heat pump, for example, or a compressor. I don't mean one of those, I mean like a refrigerator. It's pumping the heat out from the cold space in the fridge to the outdoors. How easy is it to do that? If it's really cold outdoors, well then all you gotta do is just be like, hey, here's a little bit of heat, and it's like, yeah, no problem. It's a vacuum for it, a little swish, right? But if it's really hot outside and you're trying to pump more heat out there, that's a little tougher, right? That's like trying to pump water into an already full barrel or a nearly fuller barrel. Whereas if the level of the water is way down here, you just go, oh yeah, there you go, and no problem, right? But if the barrel's almost full and you got only a little bit of room, right, you're soon to fight the pressure difference that's kind of impeding you from pumping water into it. So during the wintertime, better efficiency in the refrigerator, less cost of the refrigerator. But this is for the outdoor refrigerator. Who has those? Well, this is all what we do for you. It's investigating, real applications. Okay, so we will call it good here. I think we are just about done for today. So happy rainy day, at least it is here today, a fairly rainy day, but I think it's supposed to clear up and be good for the rest of the week. So run between the drops. Actually, if you had 4A with me, you should know that it doesn't matter if you run or walk, you're gonna get equally wet. So happy rest of your day, and we will see you tomorrow.